Okay, so once now we have concluded the part of devoted to the description of the estimation methods, now we need to understand, if you remember the scheme that will be recalled in the next slides, how we can determine if the order you have assumed is correct, and especially the validation. So remember the sentence, a model is of no use if its validity is not verified. Something that is useless if you cannot validate it. So choice of the model structure. So type which kind of model. Normally you have at the beginning, you start with, for example, a linear or nonlinear. In the identification toolbox, we will see you can select both linear or nonlinear. Normally, we work, at least in this course, we are identifying a linear system because it's something that is a way for deriving. It will be our reference that is linear. Of course, you can select black box, so completely unknown means in the parameters, or white box. White box means that you know the structure and the parameters. In the middle is not written here, but is gray box, something in the middle. It means that perhaps you know the order, for example, you don't know the parameters, but the structure is known. The gray means in the middle. Box, black box, you don't know anything. White box, you know everything. In the middle is gray. Of course, it's important the size of the model set, the orders of the polynomial. The size, it depends on the model set, how many families or classes of models you need to consider. The orders, of course, remember, no true order in the reality. True is a quotation. True, there is nothing. True, nothing is true. The real is not. We don't have a true order. Model parameterization, we can, of course, transform the data, we can refilter. Also, there is a choice of the operators. Well, in our case, we are always considering this is for discrete time, but there are some other approaches that can allow to estimate a continuous time model. Well, it's not our case because we are assuming that we have sample data, everything in the discrete time. Objective is very important. It's something that you need to focus. So a good model, of course, good in the sense, again, is a quotation. Low cost is something that low, well, the cost in the sense of time, because you want to derive it in very, very quickly, or in terms of money, because you are expanding, you need to, for example, employ some other colleagues that who help you to in the estimation, in the derivation as a team, so it can be quite expensive. quality of the model. So is a measure, a scalar measure of, let's say, goodness. Normally, we will see is the mean square error, which is something, is a comparison between the real, the measure, and the prediction, or the measure, we will see, measure and the prediction, measure and the simulation. Normally, the mean square error is something that depends on two factors and has a bias contribution and a variance contribution. If you reduce the bias, it means that the difference between the real, the measure, and the estimation, it means that you have a more flexible model structure. When you decrease the variance, if you decrease the variance, you decrease the number of estimated parameters. So it's something that is, again, is a trade-off. It's a trade-off. So it should be flexible, but not too complex. So if you, for example, if you want to describe as a function, you have that, again, always you have this kind of graph. Let's say if in the x-axis you have the, let's say, p, the number of parameters, while you increase the number of parameters, of course, you improve the accuracy, so you decrease the mean square error because you are better and better describing your data, but you are losing flexibility. And you have a very complex system, too complex. On the other side, with a reduced number of parameters, you are losing the mean square error is increasing because you are losing the error. You are deteriorating your error. So we can see here not accurate. So you have again the trade-off, a trade-off here of the cost, or let's say of your order, the number of parameters, P. So you have a trade-off between the flexibility, so not too complex, and the principle of parsimony, so not too many parameters, but not too reduce parameters, not too few, because with a reduced number of parameters, you reduce also, you lose in accuracy. So something in the middle. The problem, price of the model, so which is the let's say the price. So it depends on the complexity of the algorithm, and another is the computational time and the power. And the final observation is the intended use of the model. Why you are deriving this model? What for? It depends on your application. So model validation, then we have a break. So is important, why is important to validate a model? Validate the model and its structure. As we saw in the previous slide, an underparameterized model, underparameterized means that you are considering, for example, a reduced number of parameters. So is inaccurate or not flexible. On the other hand, you have the opposite problem. An over-parameterized is too complex, it's too expensive, so it's not parsimonious, or it leads to unnecessary complicated computations, because you can see that when you increase the order of a model, you are also increasing the time required for estimating it. It takes, we tried, I don't know, some years ago, we were working on a model of a diesel engine, and it took, I don't know, several hours in MATLAB for estimating a model in a state space form with an order that was varying from 20 to 40. It was really, but you know that you can imagine that a diesel engine is very complicated. So for model validation, there are basic approaches. We will see there are very simple approaches. We are comparing some plots of signals. Common sense, another way for understanding the validity is common sense. So a priori information, the purpose of the model, and then we can have also more complicated tests. We will see them, for example, statistical tests. But as you can imagine, statistical tests are quite not always valid, because of course it's statistics, and in practice we don't have any statistics. So something that of course is true in the real world, in the fake world, but in practice it's not valid. So it's something that of course you can check, but statistical tests, we will see, I don't know if we are going to see them, but normally they fail. All tests fail when you are in real conditions, so they are not very useful. Okay, well, I think we can stop here and have a break.